Hello, everyone, and thank you for joining us for a bonus session in our 2021 Climate Action webinar series. My name is Frank Bostrom. I'm chair of the AIA California Education Subcommittee within COAT, and I'll be your moderator for today's segment. As you know, AIA California has developed an in-depth series focused on understanding and implementing the AIA framework for design excellence. This series will run through the end of this year and will feature monthly hour-long general climate action webinar programs, as well as 90-minute webinar deeper dives into technical topics. Additionally, AIA California has partnered with various organizations and like-minded goals to bring bonus content to you in the comfort of your office. As always, all webinar content and additional resources will be available on the AIA California website shortly after each session. A few quick housekeeping reminders before we get started. Today's session qualifies for one AIA HSW learning unit for those watching live, and AIA California staff will report these units for you. The session is also being recorded and will be posted on the AIA California website with additional resources and a PDF of the presentation shortly after this presentation is complete. As a reminder, please use the Q&A function to ask any questions for today's presenter. You can also ask questions and move it to the top of the queue if you're more adept than me and know what you're doing. Yeah, that works. As I mentioned earlier, AIA California has partnered with Build with Strength, along with the National Ready Mixed Concrete Association, California Nevada Cement Association, and California Construction and Industrial Materials Association, who have helped make the AIA California Climate Action webinar series possible. In addition to today's webinar, there will be a hosting of 2 more sessions on specifying sustainable concrete and concrete innovation in the upcoming months. More information on these sessions will be shared in the follow-up correspondence and is also available on the AIA California website. Today's session will focus on concrete is the building block of the modern society and the most widely used building material. Nearly every structure built today, including buildings, bridges, homes, and infrastructures, use concrete in some way. It provides us with shelter, along with places to work, learn, and play. It connects us through roads and rapid transit and airports. Water is delivered and treated in concrete structures. Concrete is economical, available everywhere, durable, and versatile. As demand for building construction continues to increase, it is likely the demand for concrete will also increase. Like all building products, however, concrete has a carbon footprint. This course will analyze the top 10 strategies to take advantage of concrete's benefits while ensuring the lowest possible carbon footprint. I'd like to quickly introduce today's presenters before handing things over to them. Lionel LeMay is the Executive VP, Structures and Sustainability for the National Ready Mix Concrete Association. He leads a team of professionals to offer building owners and designers cost-effective, durable, and sustainable concrete building solutions through education, research, and design assistance. He has written many articles and books on concrete design and construction. He is a registered professional engineer and structural engineer in the state of Illinois. He is also a LEED accredited professional. Mr. LeMay holds a bachelor's and master's in civil engineering from McGill University in Montreal, Canada. Patrick Mustache, is that right? Did I do you right? Did I do you, Judge? Okay, good. Is NRMCA's Senior Director, Building Innovations in Structures and Sustainability Group. Patrick is an expert in building operations and real estate investing. His primary objective is to offer technical expertise to developers and design professionals to incorporate resilient and safe concrete solutions into their projects. He integrates teams of architects, engineers, and contractors to offer durable, energy efficient, and economical concrete solutions that meet the needs of both the building developers and their tenants. He supports member companies by providing outreach and education to developers and design professionals, offers practical alternatives that underscore the economic benefits of building with concrete. His focus on low and mid-rise commercial and residential structures will advance the use of insulating concrete forms, tilt-up construction, and other cast-in-place framing options on the markets. And last but not least, we're going to talk a lot about low carbon. So take it away, Lionel. Take it away, Patrick. Thank you.
Thank you. Let me get my screen here. Oops. Okay. Share the screen. Share my screen. Well, thank you very much, Frank. And everyone, welcome to the webinar. Today's topic is the top 10 ways to reduce concrete's carbon footprint. I'd like to thank the AIA California for giving us the opportunity to present this important topic today. The webinar is sponsored by Build with Strength, along with the National Ready Mix Concrete Association, the California Nevada Cement Association, and the California Construction and Industrial Materials Association. Today's program is also being promoted by AIA Seattle, where the sponsors there are Build with Strength, the NRMCA, and the Washington Aggregates and Concrete Association. Okay, so again, today's AIA Continuing Education will offer you 1 HSW credit. Today's learning objectives are to understand the basics of embodied carbon of concrete, evaluate the immediate steps that can be taken to reduce carbon footprint when specifying concrete, prioritize design strategies to get the greatest reductions in carbon footprint using current technologies and design tools, and of course, to explore how innovative technologies will result in zero carbon concrete in the future. Concrete is unique for many reasons. Its formulation is highly influenced by its application. Design professionals and contractors have a greater influence on concrete formulation than they do on any other building product. Concrete can be made stronger or weaker, lighter, more flowable, stiffer, less permeable, depending upon the performance needs. No other building material is as versatile. It can be exposed to the elements or exposed for architectural reasons. Concrete is economical, available nearly everywhere, and made from the most abundant materials on the planet, and usually it's locally sourced. Concrete does not rust, rot, or burn. Concrete is used in nearly every structure where people live, work, learn, and play. It's used for the largest buildings, the longest bridges, the tallest buildings, the busiest airport, the most efficient rapid transit systems, roadways, theaters, stadiums, schools, apartment buildings, and of course, houses. Drinking water is transported in concrete pipes and reservoirs, and waste is treated in wastewater treatment plants made of concrete. Concrete is part of the infrastructure that connects us. It's a material that helped build modern society and will likely be part of improving modern society for some time. According to the UN Environment Global Status Report of 2017, the world is projected to add approximately 3.4 trillion square feet of new buildings by the year 2060. That's an area equal to approximately 1.5 times of the current global building stock. The UN report urges building designers and owners to design disaster resilient buildings for the future with zero energy consumption. At the same time, the UN report also urges the building industry to reduce the embodied impacts of the building materials they use. Because of its thermal mass, concrete has long been the material of choice for energy efficiency, and because of its strength and durability, it has been the material of choice for disaster resilience. The challenge is to offer these concrete benefits with a lower carbon footprint. This presentation will discuss how design and construction teams can implement 10 simple strategies to reduce carbon footprint today. The recommendations are listed broadly in order of priority, but not in the order of impact reduction. All are important and all should be implemented. In addition, the strategies are meant to achieve a lower carbon footprint without impacting other traditional performance criteria for concrete. Let's start with the top 10 things you can do to lower concrete's carbon footprint. Then I will go through each one in detail. Communication. Communicate carbon reduction goals. Ensure good quality control and assurance. Optimize concrete volume. Use alternative cements. Use supplementary cementitious materials. Use admixtures. Do not limit ingredients. Set targets for carbon footprint. Sequester carbon dioxide. So the most important step is communication. One of the basic tenets of achieving a goal is to effectively communicate that goal to everyone on the team. For concrete, this is especially important because there are so many parameters and criteria for concrete mixes. To make sure that reducing embodied carbon remains a top priority throughout the project. Reducing the embodied carbon must include in drawings and specifications that are communicated to the owner, the contractor, and of course the product suppliers. We have three basic recommendations. The first is to collaborate. The only way you can set carbon footprint goals is to understand the capabilities of contractors and the producers who will work on the project. Invite them in for the meetings with your design team. Understand technologies and concrete ingredients that are available locally. Just because a product, we'll use slag as an example here in California, isn't generally used in the market, it doesn't mean you should not specify a product or prohibit its use. Generally, the reason a product is not used is because there is no demand for it. You need to create demand by permitting and encouraging its use. Next, specify your goals or targets. State your goal at the beginning of the concrete specification. In section 03300 of the specifications, part 1, make it clear what level of carbon reduction you're trying to accomplish for the project and for the concrete itself. Communicate early and often in pre-bid meetings. Are you all getting the sense that communication is the key to lowering your carbon footprint? It's important to communicate carbon reduction goals in other ways as well. Most projects have pre-bid meetings, which can be opportunities to communicate carbon reduction goals for all products to potential bidders. Concrete producers design concrete mixtures to meet the needs of the contractor in terms of workability, which includes flowability, pumpability, finishability, etc. And based on their local aggregates, and then using a sufficient quantity of cementitious materials to achieve the required compressive strength, which is higher than the specified compressive strength. This over design, the difference between actual average compressive strength and the specified compressive strength, is based on well-established statistical models described in the codes and standards for concrete. There are well-established procedures for taking concrete samples, preparing test specimens, storing them on site, transporting them to a laboratory, and finally testing them in a compression testing machine or other apparatus. Keep in mind, it's very important that concrete rarely tests well when testing protocols are not followed. One way to provide some assurance that a concrete producer has a good quality control is to require certifications for their manufacturing facilities, their mixer trucks, concrete technicians, and finally for plant operators. The same can be said of installers and independent testing laboratories and their personnel. In the quality assurance section of the concrete specifications, that installers are ACI certified, concrete producers have their plants and technicians certified as well. The same principles apply to testing labs. Make sure they are qualified and make sure that their personnel are certified. This strategy, optimizing concrete value, is just about employing good design practices. If a structural element such as a concrete column or beam is designed larger than required, then excessive concrete is being used, which of course increases embodied carbon. Alternatively, for a high-rise building, reducing the size of the columns might be critical to keeping the rentable square space to a minimum. This means using high-strength concrete, which generally means a higher carbon footprint. We suggest using a life cycle analysis software to quickly calculate the embodied carbon of the concrete elements, structural and architectural. Consider exposing concrete whenever possible. Finished materials have a considerable carbon footprint. And since exposed concrete can be both attractive and is fire resistant without the need for additional protection, this is an excellent strategy for reducing the overall carbon footprint of the building. And of course, another benefit of leaving concrete exposed is that concrete absorbs carbon over time through a process called carbonation. We're going to talk a little bit more about carbonation a little bit later in the presentation. So our first case study is 960 West 7th in Los Angeles. It's a multifamily high-rise development located in the heart of downtown LA. This 64-story office tower has 784 residential units, totaling 870,000 square feet. The challenges? Projects of this magnitude have challenges when it comes to balancing cost, long-term value, energy efficient, occupant comfort, and of course, sustainability. This design team, the developer, the contractor, the product suppliers, need to have the same goals in mind when it comes to reducing environmental impact, including their carbon footprint. The sustainable solution was to design an efficient and effective structural system. Structural engineers play a key role in selecting the structural system for most buildings, especially for a high-rise building in a high-rise seismic zone located throughout California. In working with the design team to best meet project goals, the engineering firm proposed cast-in-place post-tension slabs with a centralized buttressed concrete core that tapered with height. This system optimized floor-to-ceiling heights, eliminated transfers, and worked with residential and public spaces to optimize the net and the gross floor ratios while preserving the unobstructed views of the building perimeter. The firm's optimization also included performance-based seismic design, 80 KSI rebar, wherever it led to a material reduction. So they were able to reduce their carbon mass. So the design team set targets for carbon footprint and used life cycle assessment software to evaluate a benchmark building against a proposed building. Again, we cannot stress enough the importance of early communications and engagement with the contractor, the concrete supplier early on also helped tighten up the mix designs, where the single challenge of the aggregate being used, moving to an imported and high quality aggregates, improved quality control, variation in the mix performance, allowing the same specified compressive strength, reliability to be achieved with a lower quality of cementitious material. The structural engineer worked with the contractor to determine where faster strength gain was really needed and adjusted testing age accordingly to accommodate the higher volumes of SEMs. The design team reduced 24% of the total project embodied carbon footprint at zero cost add. There was no cost add at all. And that's after accounting for the carbon from barging aggregate from the Pacific Northwest down to LA. On the PT slab mixtures alone, they reduced the carbon footprint of the mix by 47%. And with that, I'd like to turn the presentation over to Lionel LeMay, Executive Vice President of Structures and Sustainability at the NRMCA. Lionel?
All right, thank you, Patrick. Excellent
Thank you.
presentation. Let me go ahead and continue on. So this is strategy number 4, which is use alternative cements. There are several alternates to Portland cement, but the most common are called blended cements. These combine ordinary Portland cement with other materials. The most common type of blended cement is Portland limestone cement, often called PLC for short, but technically it's ASTM C595 type 1L cement. This blended cement combines up to 15% limestone interground with Portland cement to make a cement with a carbon footprint that is up to 10% lower than ordinary Portland cement, with performance that is identical to, and in some cases, better than ordinary Portland cement. There are 4 types of blended cements under ASTM C595, ranging from type 1L cement to type 1S, combining slag and Portland cement, type 1P, combining a pozzolan like fly ash with Portland cement, and type 1T that combines 2 of these constituents with Portland cement. Now, both ASTM C595 and ASTM 1157 have been permitted in national standards such as ACI 318 and ACI 301, ASTM C94 for ready-mix concrete, and in the building codes for at least 2 decades. But most project specifications inadvertently prohibit their use by not listing them in the specification. The solution for this one is easy. Just list all 3 types of hydraulic cement in your specification. If there's one thing that you take away from this presentation, I would say make sure you go back to your concrete specification and check to see that you permit ASTM C595 and ASTM C1157 for hydraulic cements. Obviously, you're going to want to check with your structural engineer as well, but make it clear why you want to include those cements as part of the specification, mainly to reduce carbon footprint. But also, they perform well in structural applications. The next strategy is to use supplementary cementitious materials. Nearly all concrete used today has some amount of supplementary cementing materials. The most common are fly ash, slag, and silica fume, in that order. However, there are others such as metakaolin, volcanic ash, rice husk ash, and ground glass, just to name a few. Some are waste byproducts and others of industrial processes, and others are natural materials that require little processing and therefore have small carbon footprints. And the beauty of these materials is that they all enhance the performance of concrete when combined with Portland cement, including increased strength, increased durability, and enhanced workability. There's a complex chemical process that occurs between the SCMs and the Portland cement hydration byproducts in concrete, which contributes to these enhanced properties. The solution here is simple. It's in the specification. Just make sure you permit all types of supplementary cementing materials in your specification. There's no need to provide limits on SCMs. There are some limits that are required in the code or required by code, but those are typically required for exposure conditions that include freezing and thawing. But for most applications, especially for buildings that are not exposed to extreme conditions, that there really isn't any need for a limitation on these supplementary cementing materials. Our second case study is the University of California, San Diego, North Torrey Pines Living and Learning Neighborhood. It's 10 acres of academic, residential, and commercial buildings, housing over 2,000 students. The biggest challenge here is, of course, to meet the University of California system's sustainability policies. Most structures at least have to meet LEED Silver. Many of the projects need to meet LEED Silver. It's recommended to meet LEED Gold, and this project was slated to achieve LEED Platinum. And if you're familiar with the LEED system, when you're trying to achieve LEED Platinum, you really need to achieve almost all the credits in LEED to get that level of certification. So you need to implement a lot of their the LEED green building strategies. Among many other sustainable solutions for this project, the biggest one was that they required that life cycle assessment was used by the team bidding on the project to demonstrate sustainable design outcomes. And one of the outcomes was the use of type 1L blended Portland limestone cement with 13% limestone. So the project did use over 31,000 metric tons of type 1L Portland limestone cement, which could save over 3,000 metric tons of CO2 on the project, the equivalent of 664 cars removed from the road for 1 year. The designers also exposed concrete for aesthetic reasons, but also took advantage of concrete's ability to absorb carbon dioxide. Through collaboration and open discussion, the project teams were able to determine the aesthetic, structural, and environmental benefits of the concrete on the project. And the addition to CO2 reduction, the use of Portland limestone cement also enhanced the appearance of the exposed concrete. You can see from this image here that in this case, the PLC being used on the project resulted in a relatively light colored concrete, consistent light colored concrete. Strategy number 6 is to use admixtures. Again, nearly every concrete made today uses some sort of admixture. Most affect the plastic properties in order to make concrete more workable, economical, shorten or lengthen set time, and so on. And without admixtures, concrete could not be pumped hundreds of feet in the air or transported hundreds of miles, and many architectural finishes could not be achieved. There are water-reducing admixtures that in effect reduce cement demand. There are accelerators that improve strength gain, and viscosity modifiers that permit concrete to flow into very tight spaces, amongst others. An example of how effective an admixture can be, making concrete perform better, is also reducing carbon footprint. So let's take a water-reducing admixture that reduces water content in a mixture by 12%. This will result in a reduction of cement content by about 70 pounds per cubic yard for the equivalent slump and strength that you were targeting, which results in a carbon footprint reduction of roughly 10%. And that's for a 4,000 PSI concrete, might be more for a higher strength concrete. There are also high range water reducing admixtures that can reduce water content by as much as 40%, but the potential reduction in cementitious materials may not be feasible because of other constructability needs, but the point being is you can likely go higher than 12%. Here's another simple solution. Basically, allow for all admixtures that meet the ASTM standards to be permitted on the project. And you should also consider admixtures that don't meet an ASTM standard, so long as there are proper submittals and technical backup. Again, this comes to this idea of encouraging innovation. Only because admixtures are being developed all the time, and there's no way oftentimes for them to quickly, they typically always end up getting a standard, but in some cases, possibly not. It just takes a long time, as you know, to meet a standard. Number 7, a little more difficult, although it just requires some diligence from your specifiers, and that is don't limit ingredients. The tendency is to try to limit certain ingredients in concrete, and really that does limit the concrete producer's ability to meet performance criteria, let alone reduce a carbon footprint. Let me explain. Oftentimes we see specifications that have limits on water to cementitious materials ratio. In most cases, requiring a maximum water cementitious materials ratio is unnecessary and drives up cement content. There are times when a maximum water cementitious materials ratio makes sense, mostly for cases of concrete exposed to freezing and thawing, but it's not necessary to actually call it out in the specification. Identifying the exposure class of the concrete per ACI 318 and 301 will suffice. The requirements for water cementitious materials ratio for concrete exposed to freezing and thawing are all outlined in those specifications. The same is true for air content. It's only required for concrete exposed to freezing and thawing, and air entraining decreases concrete strength. For instance, a 10% increase in cementitious materials content for 4,000 PSI air entrained concrete compared to non-air entrained concrete for the same strength roughly translates to 9% increase in carbon footprint. So if you're unnecessarily using air entraining admixtures in some mixtures, you're unnecessarily increasing the carbon footprint and strength and wasting cement, which is, what makes concrete so valuable. Do not list a maximum or minimum cement content, maximum or minimum SCM or supplementary cementing materials content, or quantity of admixtures. Do not limit water used for making concrete to potable water. Believe it or not, there is an ASTM specification for water used to make concrete that addresses all the health and safety needs, but you don't necessarily need to get water out of a tap to make concrete. The recommendation here is to provide a table in the specification for concrete listing the important performance attributes for concrete. Each project will have different values depending on project requirements. So for this example, class 7 concrete, which is exterior pavements, that would have a water cementitious materials and air content limit based on the exposure class. You can see here F3 is what triggers it. That's because it's exposed to freezing and thawing and has some de-icing chemicals being placed on it. And finally, concrete that won't be stressed for significant time periods can be tested at later ages, which means higher volumes of supplementary cementing materials can be used, resulting in lower carbon footprint. So that, for example, class 1 concrete mat foundations, you can see the F'(C) requirement is 6,000 PSI at 90 days. Which means you can use a much higher SCM content. Number 8, set targets for carbon footprint. This strategy is for those who have some knowledge of life cycle assessment, experience with environmental product declarations, and an understanding of global warming potential for the targets to be implemented effectively. But most teams now working on a project that has a carbon footprint goal will likely have somebody who understands life cycle assessment and the tools used for doing those evaluations. First, you want to resist the temptation to set carbon footprint limits for individual classes of concrete. In other words, you don't want to have each class of concrete or mix on a project with a carbon footprint limit. In effect, this is the same as providing prescriptive limits on materials and leaves little room for the contractors or the contractor and producers to innovate and meet the project performance requirements, including things like budget and schedule. The best approach is to use a whole building life cycle assessment to set a carbon budget for all the concrete on the building. And for that matter, if you're working on a lead project that has, whole building life cycle assessment or trying to meet that credit, you're going to probably want some carbon budgets on some of the other materials too on the project or end products. Now, it's still necessary to have a general idea of what the carbon footprint of each mix will be to set a carbon budget for the building. And although we won't get into the details of that today, our second presentation coming up in May, we'll get into a lot of the detail on how to do that. So here's an example of how you might want to specify a carbon budget. You can see on the slide here under concrete materials, supply concrete mixtures such that the global warming potential of all concrete on the project is less than a number. It's not just an example here because you would have calculated what that number needs to be in advance using the LCA software. Many concrete companies have published EPDs for concrete, and most are willing, especially working on these high-profile projects willing to publish EPDs, especially within the spec, right, for a project. NRMCA has published a cradle-to-gate life cycle assessment of ready-mix concrete and industry-wide EPD for concrete. And armed with that information, you can conduct an LCA to determine the embodied carbon impact of concrete of a benchmark building, and then running the LCA software again for the proposed building with different formulations, right? High volumes of SCMs, admixtures, and all the things we talked about. Even using some of the alternative cements, blended cements that we talked about, and comparing that to the benchmark building. And then you can begin to set your carbon budget based on those calculations. So this is our next case study. This is the Oracle Waterfront campus in Austin, Texas. It's a relatively large office building, 550,000 square feet, ground level parking of 150,000, and a large parking deck of 650,000 square feet. In this case, the building team was, and construction team, design team and construction team was challenged to have the project blur the lines between the public and private property and be welcoming to the pedestrian-friendly community that surrounds it, while meeting the challenges and sustainability criteria of LEED and the Austin Energy Green Building standards. So the structural engineers worked closely with the design build team to meet the demanding schedule, structural challenges, and environmental criteria for this project. The design required oversized floor plates to accommodate open office spaces, expansive balconies and terraces, and large meeting spaces. They also made the designer's vision for a truly unique lobby space come to life with a floating stair and bridge that leads visitors to the large meeting spaces. So the structural engineers conducted a life cycle assessment using software which considers the embodied impacts of all materials of the structure and enclosure for the project. Since this was such a concrete intensive project, they focused on improving concrete mix designs to meet the LEED whole building LCA criteria for lowering environmental impacts. They created 2 computer models to compare the proposed building to a baseline building, fully maintaining the functional equivalence of the 2 buildings, but varying the mix designs. The improved mixes were analyzed by the software to determine the embodied environmental impacts per cubic yard. And based on that analysis, the concrete mixes were implemented into the whole building LCA. They also varied the age for testing concrete to allow for higher volumes of fly ash. For example, since the foundations did not see the full loads until much later in the construction process, they did specify testing concrete at 56 days for the drilled piers. And as a result, the project met the rigorous LEED whole building LCA credit by showing at least a 10% reduction in global warming potential, 12% in this case, along with at least 10% reduction in at least 2 other environmental impact categories. Now keep in mind, this is not just for concrete. This is for all of the structural and shell exterior envelope components of the building. So the concrete, to meet those criteria, typically you have to have a pretty significant reduction in the carbon footprint of concrete. This is strategy number 9, which is sequester carbon dioxide. Because there's a lot of concrete used on many projects, if we can sequester carbon dioxide in concrete, it's a great way to permanently sequester that atmospheric carbon. Now, carbonation is a naturally occurring process by which the CO2 penetrates the surface of hardened concrete and chemically reacts with cement hydration products to form carbonates, basically turning back into limestone. For in-service concrete, carbonation is a relatively slow process with many dependent variables. The rate decreases over time. And this is because carbonation decreases permeability and carbonation occurs from the surface inwards. creating a tighter matrix on the surface that makes it more difficult for CO2 to diffuse further into the concrete. While slow, the carbonation process does result in an uptake of some of the CO2 emitted from cement manufacturing, a chemical process called calcination, where CO2 is emitted. Theoretically, given enough time and ideal conditions, all the CO2 emitted from calcination could be sequestered via carbonation. We don't necessarily have ideal conditions, but obviously exposed concrete's a big part of it. In the specification, I would say, consider permitting the use of recycled aggregates made of demolished concrete on a project, and possibly require those recycled aggregates be exposed to air for 1 year before being used. Now, this idea works probably best when you're, revitalizing a site, maybe taking existing structures, demolishing them. You can take some of that aggregate, let it stand for a while before the construction starts, and then use it as part of the project. And the reason why that works so well is that carbonation happens accelerated when you have a high surface area to volume ratio. So crushed concrete, high surface area to volume ratio, you can get carbonation happening at a relatively high rate. You can use recycled aggregate in some structural applications. Usually we've done some testing, and there has been some testing where you could use up to, say, 10% and really not affect the performance of concrete. Now, I'm not talking about using 100% recycled aggregate in concrete necessarily, but using a small portion of the aggregate as recycled aggregate. And then permitting that you at least require all the aggregate base and any fill materials used on the site be from that crushed concrete that's already been exposed to air, which would then sequester that carbon dioxide that it would have absorbed during that period. There's also new products on the market, relatively new products on the market, that take advantage of this natural process of carbonation. So you can use things like injecting CO2 into concrete when it's being made, or you can cure concrete under CO2 environments. And also there are some companies that are now working on producing artificial limestone aggregates. Some of these technologies are more commercialized than others, but I think we're going to see, because of the interest in lowering concrete's carbon footprint and just simply lowering embodied carbon of buildings in general, you're going to see some of these companies really start to be used more and more often, or these technologies. Again, I'm going to repeat the fact that using exposed concrete on the project, both for interior and exterior applications, is a good idea if you can do it. This has the added benefit of reducing the amount of finished materials, as I mentioned before, in addition to absorbing CO2 throughout the lifetime of the building. This is strategy number 10, which is to encourage innovation. Now, of the 10 strategies, this is probably the most challenging. Throughout this presentation, I've talked about the importance of not listing specific products or naming certain technologies in the specification. Instead, simply list the standards that one must meet. But the problem with that is, of course, that it does permit innovation, but it does not necessarily encourage it. And many innovations might not meet a current standard. So this really goes back to strategy 1, which is communicating your carbon reduction goals early on, so that the contractors and producers are given basically some license to look at some of those innovative solutions and offer them early on during the design process. Design charrettes, and I realize that concrete producers and contractors are typically not part of design charrettes, but this is a whole different ballgame now. We are in an area where we need to have the entire team involved in providing solutions. So that would be a great place to start. Encourage your engineers, contractors, and producers in the area to come into the design process to offer these solutions. Most sophisticated producers today that would be working on some of these higher profile projects are experimenting on new formulations all the time. you want to ask them to discuss some of their low carbon concrete solutions. So there's no silver bullet to make concrete with zero carbon footprint. I think in the future, we're going to see it. Now it can be done for small amounts of concrete. We've seen concretes being made with zero carbon footprint, or even carbon positive, but not at the volumes and cost demanded by today's building owners. And some of these large projects, the ones that we showed you, in these case studies, you're not going to have zero carbon footprint for all the concrete on the project, but you might have some that's 90% reduced from a benchmark or from average, and others that are closer to 70%, and still others around 30%. And all these reductions lead to concrete with a significantly lower carbon footprint than similar projects. If you choose to set a carbon footprint or carbon targets, this will lead to the greatest reductions, but it always refer back to these top 10 or this top 10 list when implementing ways to reduce concrete's carbon footprint. With that, I just want to mention, and it was mentioned early in the presentation here by our hosts, that we have 2 other presentations coming up, specifying sustainable concrete on May 5th, concrete innovations, that basically these 2 presentations leap from this presentation to get into some of the detail. I know everybody loves to hear about specifications, so I'm sure we're going to get a huge crowd for May 5th, but I encourage you to maybe get some of your consultants to come, some of the structural engineers you work with, come to that session to hear about how we can specify concrete to lower carbon footprint. And then we're going to talk about some of the concrete innovations we talked about. Didn't really talk a lot about some of the concrete innovations that are being used today in this presentation because there's really not enough time, but we really wanted to talk about what you can do today, without some of these, very innovative products. In the future, I think we're going to see a lot of these innovative products being used. But for now, if you want to, tomorrow, if you want to start writing your specification or reduce carbon on a project, that's what this presentation was about today. And then finally, Build with Strength will be the presenting sponsor for the Monterey Design Conference, the online conference, October 21 and 22. And you can get more information there at the montereydesignconference.org website. So with that, Frank, I think we do have time for questions if you'd like to ask us some questions.
No problem, right away. Well, one of the first ones that come up has to do with LCA software. I don't know if there's certain softwares that you prefer to work with or don't work with. I saw Walter P. Moore's name up there, and they're certainly very sophisticated runs that they make. Do you guys have a preference for LCA?
Well, so I won't necessarily tell you a preference. Now, when we do LCA here, we use the Athena Impact Estimator, and if you just Google that, you'll find it. And probably the reason we use it, it's free. And a lot of our mix designs that we did with the benchmarks and the industry IDBD are already embedded into that software. It's relatively easy to use, and again, it's free. I would say most of the sophisticated engineers who are running LCA or architects that are running LCA likely use Tally, which is a plugin to Revit. And so, Walter P. Moore, MKA, that did the high rise in LA, they use Tally software, but and most architects, I would say, probably use Revit now. And so getting that plugin might be the way to go. The good thing about it is all the data for material quantities are already there, right? So you don't have to repeat that step. You can in the softwares import material quantities, but it's an extra step that you might not want to use. Now, OneClick is another example of software. I haven't used it. We've been meaning to experiment with it. They do have a free version now, not as sophisticated maybe as some of the more sophisticated versions of that software, that is that you can purchase. And I don't know, honestly, my guess is that there's a way to import data for quantities, but again, I know that there are some who swear by one click. So those are the three that I am aware of that are being used.
Very good. I know you mentioned on the first run, they usually work with the defaults in the program. And then after that, you come back and run the second run with the actual mixes you want to put in there. So that makes the final numbers come out where you want. So it's a two-step process. Got a question
Yes.
here. How many days did they have to wait for the curing of the 47% cement reduction? We always like to start work right away after a pour, but you have to wait.
So I don't know the answer to that question, but I know that it was probably not very long. And I think we're moving towards this idea that, of course, for post-tension slabs, I've seen requirements by the contractor to have, 3,500 or 4,000 at 18 hours.
Right.
My guess is there may have been some compromise on this project, but maybe not. Part of it is because they did use that, higher quality aggregate that permitted a lower cement content, but still, it didn't have as high a SCM replacement content, and therefore met the requirements for post-tension.
Very quickly, you mentioned SCMs. That's an acronym for?
Supplementary cementing materials. So fly ash, slag, silica fume, metakaolin, rice husk ash, ground glass.
Okay. I think you gave some here, but where can we find examples of specifications using alternative cements available? That's, you gave us a little list here earlier, I think. No?
Well, so we do have a guide spec that we can, I wish I could tell you exactly where it is on our website, but I can provide that. If you contact one of us, either Patrick or myself, we can provide that. We can send that. We could even provide it. I don't know if we can provide a download as part of this the recording, Hillary.
Yeah, we can include it on the website.
Okay, let's do that. So it's a guide spec, and it has a section on cements that would include the blended cements that we recommend.
Okay, what has been the reaction of the building departments and building code officials to low carbon concrete? You've had any pushback?
I've not seen any pushback. Some of the most restrictive are probably DOTs that don't deal with buildings very much, but they usually have some fairly outdated specifications, and maybe they're conservative and don't look at new products very often. But that said, with states now and different communities looking at having some requirements for low carbon concrete, that's opening up the idea that, okay, if we're going to do that, then we have to take a look at our spec. But for building construction, it hasn't really been an issue that I've seen.
Yeah, I haven't. Okay, this is interesting, but it's a good question. Are you aware of any negative indoor air quality impacts caused by exposed concrete with fly ash or other supplementary materials? Because when you start putting all these additives in there, the question is there effervescence that comes out that might affect indoor air quality or something?
No, not. The only things that might cause some of that would be, if you have, let's say, high polished floors, and you're putting some chemical polish on it or something like that. And you don't necessarily need to do that, what are sealants and so forth. When it comes to the other constituents in concrete, There really isn't a health issue, and LEED actually lists concrete as a default material for low indoor or for indoor air quality materials, because it just doesn't off-gas. They're chemically
Right.
bound.
Yeah.
And I think there's a misperception about fly ash too, that there's some chemical constituents in it that could cause harm. You know what? Every building product does.
Yeah.
And the tests are, fly ash has the same constituents as, the soil in your front yard. It has some mercury in it, just like the soil in your front yard. It has some other, materials in it, but not to a higher level than, sort of surrounding levels.
Okay.
But it's chemically bound in concrete.
This one's kind of a comment, but it's good. Curing, wet concrete, internal curing, silica admixtures, protecting concrete while it hydrates, reduces permeability and increases strength. And they were hoping that maybe in the upcoming presentations, you might be able to address that a little more. Okay, here we go. For decades, we have known that natural carbonization process, movement of carbon front, moving towards the rebar, gradually changes the base acid balance surrounding the rebar, leading to rusting and rust jacking. How does adding carbon to the concrete affect this process? Is deeper coverage of rebar needed, or coated rebar need to be used? And it, to prevent it.
When I talked about carbonation and the limitations on how much you can have during the life of the project, right? And it's because if you have good quality concrete that's already relatively, or has low permeability, which is typically the case when you have supplementary cementing materials, fly ash, slag, and so forth, it's so impermeable that it stops relatively small distance from the surface. It is a problem though if you have low permeability concrete, in other words, poor quality concrete, that you can get carbonation all the way to the rebar. That you don't want. But there are other reasons why that structure will probably deteriorate before the reinforcing begins to rust, right? So if you have a parking deck or a bridge deck or something along those lines that has poor quality concrete, it's likely going to deteriorate way before carbonation has an effect on it.
I think my experience has been that as low carbon concrete with all the admixtures is coming about, your slab thickness is also being reduced somewhat because of the higher strength. So that's interesting.
Sure.
How can you make fly ash concrete less sticky to work with and not set up so fast? That's
I'm not aware of the setting up so fast. Stickiness, again, it's admixtures really are the key to that typically. Most producers working with the contractor should address that issue. And maybe in slabs where you're actually finishing it, that would be another reason that you might have limits on SCMs in slabs, right? Not only for post-tensioning to get early age strength, but for finishing purposes, there may be some limits. And that's why I propose this idea of providing a carbon budget, because now the contractor and producer team can say, okay, listen, we need a carbon footprint, or excuse me, a mix design that has a carbon footprint that's higher on the slabs only because we have these other performance criteria, finishing, post, higher strength, whatever. But we're going to go to the other limit with really high, lower carbon footprint on things like the mat foundation, the shear walls, the columns, and everything else. And if you try to resist that tendency to try to limit carbon footprints for each individual mix design, if you do that, if you do provide those limits, then you may force a sticky
Right.
you know, concrete, because the producer and contractor have no flexibility to meet that requirement.
Yeah, well, that's part of the discussion, workability. Many times, acid wash concrete is a desirable for landscape surfaces and so on. Is there a more environmentally friendly way to obtain this type of finish without the acid wash? I mean, if you get
I
into
don't know
the
the answer.
yeah, we get
Patrick, do
into
you know the answer to that question?
No, I don't.
it's, okay. How much time we gonna go, Hillary? We got a couple more here.
Maybe one more question and then we can have Lionel and Patrick answer the questions offline and we'll include those on the website as well.
Let's try here. Let's see, policies. All right, we'll ask a tough one. I'm not familiar with this product, but is Biomason a real alternative to concrete?
Mason. I don't know.
I'm not familiar with it, but
Patrick, does that ring a bell?
No.
You know, I mean, there are other, you know, hempcrete is an example of a concrete that goes beyond just adding, you know, hemp fibers to concrete. So there, you know, I think there are some alternatives to concrete that can probably coexist with concrete. Concrete has, you know, certain advantages. My guess is you're not going to use masonry for, let's say, you know, 960 West 7th.
yeah,
But, you know, maybe for some, you know, home building, you know, if you're looking at, you know, fire resistant home building technologies, that maybe that might work. Now, I may have the total wrong idea of, you know, maybe there are some bio cements out there that can be used to make concrete that might be being developed in the future. So I may be off base with that one.
yeah, okay.
It's like a paver technology, perhaps.
One of the things that always comes up, and we'll do this the last question here. When it comes to cracking, with all the additives and things that we're putting in here, reducing the carbon requires a lot of additives. So now we get into, we're controlling water in the admixture. You know, in the end, cracking is always what the major concern is. So because I'm going with a lower carbon footprint, are there more steps I have to go through to control cracking in the curing process in order to get some of these finishes that Walter P. Moore is showing?
So generally, I mean, yeah, there are potentially things like higher shrinkage with high volumes of slag, for example. So a bridge deck, for example, that usually has high SCM content because you're trying to get a really low permeability. Because of that, you can potentially have higher shrinkage, but usually higher shrinkage comes with higher paste volume. So when we talk about all of these technologies, you know, the number one strategy, and probably should have that more prominent here, is to design mixes that are most efficient. That means don't waste the cementitious component or the paste component.
Mhm.
Keep that to a minimum, right? So anybody can make concrete that has 800 pounds of cementitious materials, of which 400 pounds is fly ash. But that's a ridiculous mix, right?
Mhm.
The hardest part is to make concrete with 400 pounds of cementitious with 200 pounds of fly ash. That's
Right.
the hard part. What comes with that is a lower paste content, which likely means lower shrinkage. So generally lower paste content means lower shrinkage. As soon as you start jacking up the paste, generally you get more shrinkage. So it usually results in less cracking as a result.
Yeah.
You're doing it right.
Okay, there's a few more questions. We'll catch these offline and post the answers to them. But I would like to give a big thank you to Lionel and Patrick, our partners with Build with Strength, for your presentation today. If you've made it this far, AIA California will submit your names for CE credit, and it should appear in your transcripts in probably 10 days or sooner. There'll be more information sent out on AIA's website regarding resources and tools that are available. There'll be information be sent out to you by staff regarding the climate action series that are upcoming. And wow, I love the detail, guys. Great job. So thank everybody for attending today, and look forward to seeing you again in a few weeks for
Thank you very much, Frank.
Thank
more
you.
specifications. So have a good day.
All right. Feel free